All right. Good morning, folks. Welcome back. I want to continue on today, and I want to start our discussion of liquids. We wrapped up our discussion of gases yesterday, and so please make sure you take a look at that. We will get back to gases hopefully tomorrow. If not, we'll get back to it on Monday. I'm still trying to decide whether when I'd like to meet up with you folks next week, just to kind of get a feel for how you guys are doing. But if we have to cancel that, then I will. But I'll keep you posted on that. Okay. All right. So let's go ahead here. And what I'd like to do is number 10 has three different questions on it. And so I want you to answer the first of those three questions from number 10 to start out this morning, to give us a chance to kind of review this very important relationship between temperature, and especially temperature on the Kelvin scale, and the kinetic energy of the particle. Okay, so let's take about a couple minutes on your paper, write down what we talked about yesterday was the relationship between these two. And then I want to use this to talk about how moving forward, we can use this relationship in order to understand then how the particles behave, and the behavior of the particles, not only in the gases, but also with liquids and solids as well. There's a relationship between temperature and kinetic energy. And this relationship is going to be very important in what we can observe in terms of behavior of the particles, and thus the what we can observe on the macroscopic scale for particles in the solid and the liquid state as well. Okay, but we talked about this in the context of the gas state. So take about a minute or so, write the answer here on your piece of paper, and then make sure you submit it at the end of the period. But to go ahead and answer, let's start with this problem from your problem set. Okay. Okay. Let's go ahead and let's take a look at this question here. All right. So this question here asks us a key relationship that exists here that I think you have to know moving forward, not only for our class but also for any other science class that you will take moving forward, because I think the relationship here between temperature, okay, so temperature on the Kelvin scale, and kinetic energy is going to be very important for us in order to understand this. Okay, so let's go ahead then. And I'm sorry, let me go ahead and let's go ahead and quickly define what each one of these are. Okay. All right, so the kinetic energy, so we call this KE. The kinetic energy is the energy of motion, energy associated with the moving object. So energy of motion, okay, so motion, okay. And so any object that moves has this particular kinetic energy. Now, kinetic energy is defined, we can calculate for this. I gave you the simple formula of m times v squared. Okay, so any object that moves, it's this v squared here, which represents the velocity. Okay, that says then that if any object that moves will have this kinetic energy. Now everything has mass, but not everything has to be moving. Okay, so the object, in order for an object to have kinetic energy, okay, it has to be moving. Okay, so kinetic energy is energy that's associated with the moving object. Okay, okay. Temperature. Okay, let's go ahead and define what temperature is really quickly. Temperature is the measure of relative heat energy. Relative heat. Okay, and and that's going to be important because heat is energy. Okay, and so when we talked about the relationship between temperature and kinetic energy, essentially what we were doing is we were comparing and expressing the relationship between heat and kinetic energy. Okay, this is what we refer to as an energy transformation. Energy transformation. As the name implies, we are changing, it's a changing of one energy into another. Okay, so the answer to this question, and again, I'm providing you with all the details here, but you would have to understand this here. You'd have to understand this here in order to understand why there is a relationship between temperature and kinetic energy. Okay, so if temperature is a measure of kinetic energy, this is what we can observe. I'm sorry, temperature is the measure of heat. This is what we can observe. We can feel the heat. Obviously, today, if you go outside, it's going to be a hot day, and tomorrow, yesterday was a hot day, and from what I understand, tomorrow is going to be a hot day as well. So you can feel that heat. but temperature is how we can measure that heat. We can assign what you feel, a number and a unit. Okay, the temperature is measured in two temperature scales, Kelvin and degrees Celsius. Okay, so those are the units that designate the temperature, and then we can assign a number to it. Okay, so temperature is a way that we can observe, on a measurable scale, heat energy. So if you go out and it's cool outside, the temperature is going to be lower. Today, you go out midday, the temperature is going to be higher, which means that there's more heat. If you go out towards the afternoon, evening, or I'm sorry, evening into the early night, the temperature is going to be lower, which means then there's less heat energy around. So temperature, again, is a measure of heat energy and that we can observe. Okay, we cannot observe the kinetic energy of a gas particle or particles. Now we can observe and we can calculate and measure the kinetic energy. How? If we can measure the speed of an object and its mass, we can calculate for its kinetic energy. However, for gas particles, particles at the atomic and the molecular level, it's very difficult to observe them and measure their speed, and it's very difficult to obtain their mass. Okay, so what we do then is we obtain then a relationship that we can use, and that is this relationship here between what we can measure, which is temperature. Okay, so we can measure temperature, and so if heat is related to kinetic energy, temperature must also be related to kinetic energy. Okay, so this relationship then, and we can write it this way here, we can express this relationship in terms of a proportionality, and this proportionality symbol right here. And that is, we say then that the two are directly related. And what does that mean? It means then as one goes up, the other one goes up. So that means then what we can do then is we can say then that if we see an increase in temperature, okay, so let's go ahead and write this down here. Okay. If we see an increase in temperature, okay, what do we know then? Like we just stated, that means there will be an increase in heat energy. And if there's an increase in heat energy, because we know this is true as well, there will be an increase in the kinetic energy. And this simply stated here, folks, okay, is what you need to be able to link here. Okay, this is what you need to be able to, and you can write it out this way as your answer. You can write it out that way, or you can write it out this way as here. Okay, whereas we have then the direct relationship between kinetic energy and the temperature scale. Now, specifically, remember, the temperature scale that we need to keep in mind then, and I'm going to highlight this in red because this is, even though this is true for a temperature scale, for temperature in the Kelvin scale, Celsius scale, we have a direct relationship, between the Kelvin, the Kelvin scale and kinetic energy. Why is that? Because at the 0 Kelvin, all motion stops. Okay, so at 0 Kelvin, and we saw this yesterday, at 0 Kelvin, what we're saying then is that all motion stops. Okay? And if velocity is supposed to represent motion, okay, velocity represents how we measure the motion of an object. Okay? So then at 0 Kelvin, then the velocity, the velocity will be equal to 0 meters per second. And if that's the case, the kinetic energy is 0. And the units for kinetic energy is going to be joules. Okay? So 0 Kelvin equals 0 joules. Okay? And that is what we know is true about the relationship between temperature on the Kelvin scale and kinetic energy. Okay, so at 0 Kelvin, we have then 0 joules. So if we double, for example, if we increase the temperatures, if we notice an increase in the temperature scale, we're going to see that same increase in the kinetic energy scale too as well. So for example, if you double the temperature on the Kelvin scale, you'll see then a doubling of the kinetic energy as well. Okay, so that's what we saw yesterday, and my hope is then make sure you're able to take that with you and understand that as we move forward with this next unit here, the next section of this chapter here. Okay. All right, so make sure you come by and see me, folks, if you have any questions about that. But let's go ahead and let's continue on and let's talk about liquids. Okay, so we finished up with our discussion of gases. We talked about then what the behavior of gases. We were able to explain then the one property of gases that really makes we can experience on a macroscopic level, and that is the pressure. So we basically focused on one property of gases in the first section. Okay, and so we'll get back to that, and we'll talk about what factors can affect that gas pressure. But we'll do that in chapter 14. But we're going to turn our attention here to liquids then, and what we're going to do then is we're going to first and foremost just review what liquids are. We'll discuss it, and then we'll talk about how we can explain the behavior of liquids at the microscopic level. Okay, so here in the first part, then we're going to explain. Then we're going to develop a model for the behavior of liquids. So we're going to talk about liquids, and we're going to talk about how the liquid particles behave. Okay, in order to distinguish a liquid from, say, a gas or a solid. Okay, and then what we're going to do then is we're going to turn our attention to three properties of liquids and be able to explain those as well. So when in the first section, we just focused on one property of gases, and that is the pressure that gases exert. What we're going to do is we're going to talk about three properties of liquids here. And liquids have other properties. We won't talk about adhesion or cohesion. And so what we're going to do is we're going to focus on these three basic properties of liquids and be able to explain them. Okay, so that's what we're going to be doing in this section here. So let's go ahead then. Let's talk about what these liquids are. And I think this would be a pretty straightforward review for you folks. Okay, so we know then that liquids are a state of matter. As a state of matter, they have indefinite shape and they have definite volume. What does that mean? To have indefinite shape means then that the liquids then they will take on the shape of their container. Whatever container they're in, they will take the shape of the container, but they will not assume the volume of the container. That's what it means to have a fixed volume. Okay. A few things about liquids that just to begin with. Then the liquids are not when we talk about how the particles are arranged. Okay, so this is what we can observe. So this is on a macroscopic level here. So this is a macroscopic observation. Okay, so this is macroscopic. So when we talk about the particles here, then this is microscopic. This is a microscopic explanation. Okay, so meaning then that the particles are free to move around. Okay, they're not arranged rigidly, which means then that they are free to move around, and that's going to be fairly important for us in just a moment. Okay, so which leads to what we refer to as flowing. So the particles are free flowing. Okay, and so this here represents a macroscopic and a microscopic property of liquids that we can talk about. Okay. Furthermore, so we'll get to this in just a moment. Furthermore, then we talk about particles that are in close contact with one another. This is a microscopic observation as well. Okay. When we say that they're in close contact with one another, that means they are not packed as closely as solids, but they're packed fairly close together, which leads to a greater density than, say, with gases. Okay, so this helps us understand then why liquids are more dense than their gases, the equivalent gaseous state. Okay, so we'll talk about that in just a moment as well. Okay, we said then the volume does not change. Okay, so therefore this is a macroscopic observation. Okay, and they're virtually incompressible. Another macroscopic observation, meaning that you can't squeeze them together. And this is kind of an important property that we take advantage of. And so, for example, hydraulic lifts, the brakes in your car depend on the incompressibility of a liquid. Okay, so the liquids are compressible, but not but limited. Okay, they are virtually incompressible. Solids are not compressible. Okay, so solids are incompressible. You can't push them together anymore. Gases are compressible. Okay, so you can squeeze gases together, but there's a limit to that. Okay. All right. Finally, then we noticed in that solids, liquids will expand when heated and contract when cooling down. this is true for all states of matter, okay? And we talked about this with the liquid gases as well, and we'll get back to this when we talk about solids. But these are then some of the things that we can observe about liquids either on a microscopic or a macroscopic level. Okay? Okay, let's go ahead then and talk about a few other things about liquids before we go on. Okay, so first of all, we said then liquids are a free-flowing state of matter. Okay, what does it mean to be free-flowing? Well, if you can take a look at this picture here, what we're doing here is we're showing then that liquids can be poured out. Okay, gases can actually be poured out. We just can't see it. They flow out of the container. That means then liquids can move. Okay, liquids can move, and so we can, when we talk about flow here, we're talking about how the liquid can be transferred. It can move. Just think about a river. If you've ever seen the river move, the water is actually moving. It flows from a higher point down to a lower point. Okay, so here we have the liquid flowing. Okay, so this is a macroscopic observation, like I pointed out on the previous slide. This is a macroscopic observation because we can see the liquid move as you pour it out. Okay, so you can see the liquid pour out here. And you can imagine gases flow also, just like I said. We didn't talk about that because we focused on the pressure, but one property of gases as well is that it also flows. If you take a gas and if you have a container of a gas, if it is more dense than the air, for example, it will flow out as well. Now here, the liquid will flow out because it is more dense than the air, and so it will be pulled down by gravity. Okay, so here the liquid gets pulled down, and so this is liquid flow. This is liquid flowing out of its container. Okay? But the reason for the flow then is at the microscopic level. And so okay, this is a micro and a macroscopic observation that we can make about liquid particles. The reason why liquid particles can flow like this, liquids can flow like this, because as a particle at the particulate level, these liquid particles are moving around as well. Okay, and this is also true for gases. Okay, so we can explain then that why this is happening. So you can imagine then that this is our liquid here. Okay, so the liquid particles are moving around constantly. Okay, so they are moving around. Okay, so the liquid particles have kinetic energy. So if you can imagine, this is what's happening in one droplet. Okay, so in that liquid, the liquid particles are moving around. And we notice that with the gases as well. So this is bromine gas here. We know that bromine gas particles, they move around at a higher rate. And so the motion of these gas particles, okay, the motions of these gas particles, okay, so gas particles have kinetic energy. Okay, and so we just talked about that. Gas particles have kinetic energy. Okay, that means then that gas particles move. Okay, gas particles move, and the motion there, and we're going to distinguish the motion here with the motion of the solids. The motion here then is what we call then translational motion. Okay, translational motion. And translational motion just simply means then the gas particles can move from one position to another. And so also that's true for liquid particles. So both liquids and gases, okay, undergo what we call this translational motion. Okay, and that's what accounts for the flowing. That is what accounts for how liquids can flow. Okay, so the ability of liquids to flow and the ability of gases to flow is directly correlated to the translational motion of their particles. Okay, so make sure you keep that in mind. So let me go ahead and write this down here. Flow, what we can observe, okay, is related to the translational motion. Translational motion of the particles. Okay, and again, make sure you understand that translational motion just simply means then that an object it's going to start out at one position, and then it will end up at some moment in time at another point in space. Okay, so it moves in space. It moves from point A to point B. Okay, so it moves from start to finish. It doesn't stay in one place. Okay, so translational motion means that an object can move from one position to another. And so when the particles move from one position to another, that accounts for then this flowing nature of both liquids and of gases. Okay? Now, the ability to flow then allows then the particles then to assume the shape of their containers. So, for example, here, if we take a look at, and let me finish up here real quick, folks. If you take a look at this container here, when you pour bromine gas into it, and when you pour bromine gas into this container, you notice then that the bromine gas takes the volume, assumes the shape of the container here. So this is bromine. It takes the shape of the container itself. And so if you notice here with the liquid also, as you pour it into the container, as you pour it in from a beaker or an Erlenmeyer flask into this particular volumetric flask here, you're going to see then that the liquid's going to assume the shape of the container. Okay? So the flowing nature of a liquid accounts that it can be explained in terms of its translational motion. Okay? And so with that said, then the flowing nature, because liquids and gases flow, this is how we can explain then why liquids and gases have indefinite shape. Okay, so what I'll do tomorrow then is I will re-emphasize this connection again, and so we can say then that translational motion is then related and directly related to the indefinite shape of gases and liquids. Okay. Microscopic, macroscopic. We can observe the indefinite shape of liquids, again here, liquids and gases, and we can explain it on as a result of the translational motion of the particles. Okay, so with that said, then let me finish up here by just highlighting this for you then. What we've done then is we've taken the microscopic, we've given a microscopic explanation for a macroscopic observation. Okay. All right, folks, so very good. Make sure you you post the answer to number 10 in the problem set on today for the lecture, okay? And we'll continue with this discussion of liquids tomorrow, okay? But please take a look at the look ahead and make sure then that you can understand this relationship between what we can observe on a macroscopic scale and how we can explain it on a microscopic scale. Okay, so we'll review. Please make sure you take a look at this, and then we'll pick up with this discussion tomorrow. Okay, have a good day, folks. We'll see you tomorrow.